Scientific notation is a way of displaying very large or very small numbers. And scientific notation itself, um, you know that you've got it if you have two things being multiplied. You have the digits, the significant digits, the non zero digits, or sometimes you have to round, with just a single digit uh, and then a decimal place. So we're talking about a number that's less than 10 but greater than 0. So if I look at this number, this is not written in scientific notation, right? This is just written in standard notation. If I want to write this in scientific notation, I would be writing this as 3 a decimal point 2 times some power of 10. Well, the question is, how many times do I need to multiply 3.2 by 10 in order to make it equal 320 million? And you might think about drawing a quick line where your decimal point is, and then just count, because every single time I multiply by 10, it's going to move the decimal place over 1. So if I'm counting, I need a total of 1, 2, 3, 4, 5, 6, 7, 8. I need 8 factors of 10. So I could write this as 3.2 times 10 to the 8th power. So this is scientific notation. Um, so I can do something very similar for small numbers as well. This number again is not written in scientific notation, but if I was to write it in scientific notation, I know it would involve a 2.0, and it turns out that I need to multiply this by powers of 10 also, but powers of 10 raised to the negative 1 power. So essentially what I need to do is I need to take 2.0 and I need to divide it by 10 a bunch. And I'll just remind you that division by 10 is the same thing as multiplying by 10 to the negative 1. So every single time that I move backwards, right, I'm just going to add another 10 to the negative 1 power to it. So I might again do the blue lines here and then just count. I need to do this. If I was to divide 2.0 by a single 10, it would make it 0.2. So these are, I'm just counting the number of times I need to divide by 10. So I need to do it starting here. I need to do it 1, 2, 3, 4, 5, 6 times. So this would be 2.0 times 10 to the negative 6th power. And I might verify this by just writing the number again or just using the original one. But as I count backwards, you can see I've got 1, 2, 3, 4, 5, 6. So I definitely needed to do this. I needed to move my decimal place 6 places. And I did, and I was moving them to the left, which means I'm dividing by 10, so I've got negative numbers. Now, dealing with multiplication problems with scientific notation really simplifies the work. So for example, if I wanted to multiply these two numbers, that would be a lot of entry on a calculator, but I can do this multiplication using this scientific notation. So I've got 3.2 times 10 to the 8th power, and I want to multiply that by 2.0 times 10 to the negative 6th power. So if I look at just the digits, right, I can reorder this thing because it's multiplication, and which is commutative. So I can reorder this as 3.2 times 2.0 times 10 to the 8th times 10 to the negative 6th. If I combine these two, because my bases are the same, right, they're powers of 10, I can write this as just 10 to the 2nd power. And for me to multiply 2 times 3.2 is fairly straightforward. That would just be 6.4. So if I multiply 3.2 times 10 to the 8th times 2.0 times 10 to the negative 6, I get 6.4 times 10 to the 2nd. This answer already is in scientific notation, so I don't need to adjust it at all. And in fact, one of the things that's nice is it's easy for me to write this back into standard form. I need to move my decimal place 2 to the right because I'm just going to take 6.4 and multiply by 10 and times another 10. So 6.4 times 10 is 64, and then times another 10 is 640. So the product of this very large number times this very small number is 640. And because I was dealing with just really multiplying 3.2 times 2.0, I didn't need a calculator to do that at all. So let's look at another conversion and then another multiplication problem. So if I have this number and I wish to write it in scientific notation, I know that I'm going to want my decimal right after that leading 5. So 5.63. And then this is where I'm placing my decimal, right? I'm placing it here. So the question is, how many times do I need to divide by 10 to make this number equivalent to the one that I started with? So to do that, I might just consider this is where I'm at, and I need to divide by 10 1, 2, 3, 4, 5, 6 times. So this would be 5.63 times 10 to the negative 6th power. So this is this number written in scientific notation. And again, let's say that I want to multiply this by another number. Let's go ahead and take this and multiply it by 4 times 10 to the negative 7th power. This is going to be a fairly small number because it's a small number times another small number. So again, because this is multiplication and it's commutative, I can rearrange the factors that are going into this product. So I'll rewrite this as 5.63 times 4 times 10 to the negative 6th times 10 to the negative 7th. And I know as far as my powers go, currently this is 10 to the negative 13th power. But I need to also find the product of 4 and 5.63. And that product ends up being 22.52. 22.52, which is not, this answer that I've got, that I have, is not in scientific notation because the decimal's in the wrong spot. It needs to be here. So if I want to rewrite it, right, I can write the decimal point here, 2.252, and this number that I've just written down is not 22.52, right? It's a different number. But it turns out that if I take and I multiply that 2.252, if I multiply this number by 10, right, what I have here is exactly the same now. So I just introduce a new factor of 10. So the thing I've underlined in red above, 22.52, is the same thing as 2.252 times 10. Now, of course, I need to bring down my powers of 10 that I had to start with, so I'm going to go times 10 to the negative 13th. But now I can just deal with these exponents, right? I've got 10 to the first times 10 to the negative 13th, which is 10 to the negative 12th. So my answer is 2.252 times 10 to the negative 12th power. So this is not only the product of the original two numbers, right? This was the product also, but this is the product written in scientific notation. So if I was to do a division problem, something kind of similar happens here. Because I'm just multiplying everything in the numerator and everything in the denominator, I can identify giant ones, or I can, simplify. It turns out 12 divided by 2 is 6. So my answer is 6, and then I can use the power rules, right? 5 minus 3 would be 5 to the 8th power, or I could choose to multiply the top and bottom by 10 to the 3rd, right? I can multiply by this giant 1, and if I do that, I end up getting 6 times 10 raised to the 8th power. So if I divide 12 times 10 to the 5th by 2 times 10 to the negative third, I end up getting 6 times 10 to the eighth.